For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. Problem 1, 35%, steady-state natural circulation in a steam generation system. Saturated steam at 3 MPa, properties in Table 1, is used in a certain factory. The steam is generated by the system shown in Figure 1, which consists of a natural gas-fired heater, a riser of height L, a steam separator of form loss K, and a downcomer. The makeup flow can be assumed to be saturated water at 3 MPa. The riser and the steam separator have the same flow area, A. LiveExamHelper.com. Using the conservation equations and their constitutive relations, find a single equation from which the mass flow rate in the loop, m and, could be found as a function of the heat rate, q and the parameters a, l and k, i.e., f, m and, q and a, l, k, equals 0. 20%. 2. Find m and for the two limit cases q and equals 0 and q and equals m and hfg. Do you think the m and versus q and curve, with fixed a, l and k, could have a maximum between these two limits? Explain your answer qualitatively. 10%. 3. For a given q and, how does m and change if k increases or l increases or a increases? 5%. Assumptions. Steady-state steam separator efficiency is 1. Use HEM for the void fraction in the riser. Neglect all acceleration and friction terms in the loop momentum equation. Use the HEM multiplier for the form loss in the separator. Table 1. Properties of saturated water at 3 MPa. LiveExamHelper.com. Parameter value. Sat 234 degrees Celsius, 507 K, ρ F 822 kilograms per cubic meter, ρ G 15 kilograms per cubic meter, HF 1008 kj/kg, Hg 2803 kj/kg, Cp F 4.7 kj/kg degree C, Cp G 3.6 kj/kg degree C. Mu F 1.1 times 10-4 Pa S, mu G 1.7 times 10-5 Pa S, Kf 0.638 W/m degree C, Kg 0.047 W/m degree C, sigma 0.030 N/m. Problem 2, 55%, water boiling during a loss of flow transient in a home heating system. LiveExamHelper.com. A large condo building uses a water-forced convection heating system. The heater consists of hundreds of round channels of diameter d equals 2.54 cm and length L equals 1 m, in which water is heated by an axially uniform heat flux, Q equals 200 kW/m2, see Figure 2. The system operates at 1 MPa and the water temperature at the inlet of the heater channel is Tin equals 90 degrees C. Hin equals 365.6 kj/kg. Under normal operating conditions, the mass flux is Go equals 1000 kg/m2s and no boiling occurs in the channel. A pump malfunction occurs at T equals 0, so that the mass flux in the heater channel starts to decay exponentially, i.e. the G, T, equals Go minus T/τ, where τ equals 10s. Assume that the heat flux, pressure and inlet temperature remain constant throughout the transient. Figure 2. A heater channel. Table 2. Properties of saturated water at 1 MPa. LiveExamHelper.com. Parameter value. Sat 180 degrees Celsius, 453 K, rho F 887 kilograms per cubic meter, rho G 5.1 kilograms per cubic meter, HF 763 kJ slash kgHG 2778 kJ slash kgCP, F 4.4 kJ slash kg degree C, CP G 2.6 kJ slash kg degree C, mu F 1.5 times 10-4 Pa S mu G 1.4 G 1.4 times 10-5 Pa S KF 0.677 W slash M degree C, kg 0.034 W slash M degree C. Sigma 0.042 N slash M R asterisk 462 J slash kgk. I, using a simplified version of the energy conservation equation. Calculate the fluid enthalpy and equilibrium quality as functions of Z and T, 5%. LiveExamHelper.com. 2. At what time does the bulk temperature reach saturation? Assume the specific heat does not change with temperature. 5%. 3. At what time does nucleate boiling start? Use the Davis and Anderson model for ONB and assume that the single-phase forced convection heat transfer coefficient, H, is proportional to the mass flux, i.e., H equals HO, where HO equals 9.3 kW slash M2K, 10%. 4. At what time does a significant amount of vapor first appear in the channel? 10%. V. Qualitatively sketch the MDNBR versus time. 5%. 6. Qualitatively sketch the bulk and wall temperatures versus time at the channel outlet. 10%. 7. Estimate the time at which two-phase density wave oscillations appear in the channel. Use the stability map of Figure 3 below. 10%. LiveExamHelper.com. Figure 3. Stability map for the heater channel. Problem 3, 10%, short questions on bubble nucleation. I. A steam bubble grows at a cavity with the geometry shown in Figure 4. What can you say about the steam temperature in this situation? 5%. Figure 4. Steam bubble growing within a wall cavity. 2. To obtain bubble nucleation at a cavity of radius 1 micrometer on a copper surface, a certain fluid, of contact angle 135 degrees with copper, requires a 2 degrees Celsius superheat. What would the required superheat be for bubble nucleation at a cavity of radius 3 micrometers on steel, if the fluid contact angle with steel were 45 degrees? 5%. LiveExamHelper.com. Problem 1, 35%, steady-state natural circulation in a steam generation system. I. The flow in the loop is due to natural circulation, driven by the density difference between the two-phase riser and the single-phase downcomer. The momentum equation for the loop is where the friction and acceleration terms have been neglected, as per the problem assumptions. The fluid in the downcomer is saturated water, therefore its density is down equals rho F, while the density in the riser is riser equals alpha rho G plus 1 minus alpha rho F, 2, where alpha is the void fraction. If HEM is used per the problem assumption, the flow quality X can be found from the energy balance for the heater, LiveExamHelper.com, where it was assumed that the equilibrium quality is equal to the flow quality, a very good assumption since the riser is a saturated mixture of steam and water. Eliminating X in X 3 and 4 by means of EQ 5 and substituting X 2 and the 5 into EQ 1 gets the answer, which could be solved to find 2 if Q and equals 0, no steam, 1 has X equals 0, alpha equals 0, riser equals rho F, and therefore M and equals 0. LiveExamHelper.com.